In a cross-country meet, Lily runs 400 meters east and then runs 700 meters south. How far from where she started is she after she does this? All right, so look at that direction is east. So if we have a vector that represents 400 meters east, so this way is east, there's our vector. So we talked about this idea of vectors. A vector quantity is a quantity that requires direction. And then this arrow, right? This arrow is the symbol for all vector quantities. Now we did, just by the nature of the fact that everybody got this thing right, was an illustration that like we know our vector map. And it's really easy. I don't want to say it's really easy. I would say it is relatively easy when these vectors are representing displacements, because visually it's really easy. All right? So now what happens? Lily goes 400 meters this way, turns and runs 700 meters south. This right here was 806 meters. Now, how do we get that? That's a right triangle. We use Pythagorean. 400 meters squared plus 700 meters squared. Square root of that is roughly 806 meters. Now, again, when you do any math, make sure you put your units in. So we have lots of people missing their units. But we clearly have an idea of how to do this vector map. The vector map is exactly the same whether the quantity is displacement, velocity, acceleration, force, momentum. These are all vector quantities that we're going to work with throughout the course of the year. And our vector map is exactly the same. In other words, look at, there's really only 4 possibilities, and we've already worked with all 4 possibilities. If Lily would have walked 400 meters, sat for a rest, and then ran 700 meters more, well, she sat for a rest, she wouldn't be that good of a runner, but she would end up 1,100 meters away from where she started. If she went 400 meters in one direction and 700 meters back in the other direction, she would end up 300 meters in a different direction. Anytime you add 2 vectors in the same direction, you just mathematically add them. Anytime you add 2 vectors in opposite directions, you just mathematically subtract them. If the 2 vectors are at right angles to each other, then we use Pythagorean theorem. And what if Lily would have went 400 meters this way and then 700 meters this way? How did we conquer that already this year? What did we do? What did we do to this vector? We only did it probably once. We're going to do a lot more coming up soon. We separated this vector into what? It's parts, right? It's y part and it's x part. Right? Now, my point here is this. If we're talking about displacements, it's mathematically and visually easier to gain an understanding. But the same math works for any vector quantity. And we're now going to use this vector math with respect to velocities. And we're specifically going to use this vector math with respect to projectiles. In other words, I put this picture up there yesterday. Drew, do me a favor and describe what this picture is illustrating for us.
It's illustrating how the ball is moving at a constant horizontal velocity, but the y velocity needs to increase due to gravity. So balls.
Awesome. And how much is that y component of the velocity increasing by? 9.8 meters per second every single second. All right? Now, we have those x components that are 20 meters per second, and we have the y components that are changing. If I took my radar gun and I put the radar gun and got the actual speed of this thing right here, it wouldn't be 20 meters per second, and it wouldn't be 9.8 meters per second. It It would be the vector combination of those two things. In other words, what's happening? This cannonball at the exact same time is moving 20 meters per second this way and 9.8 meters per second down. If I can take this snapshot right here and remove it and put it over here, how fast is that cannonball actually going? Well, those are two vector quantities that need to be vectorially added together. Well, these two vector quantities are not in the same direction. They're not in the opposite direction. They're at right angles to each other. How fast is this ball actually going if at the same time it's going 20 meters per second one way and 9.8 meters per second the other way? Well, in order to add vectors, we talked about this earlier in the year, they must be placed head to tail. So 20 meters per second that way, 9.8 meters per second that way. How fast is this object actually going? Well, how are we going to do that mathematically? Pythagorean theorem. Give me an answer. What do we know? It's got to be bigger than what? Got to be bigger than 9.8. Also has to be bigger than 20, because this quantity right here, which represents how fast the ball is actually going, is the hypotenuse of that triangle. 20 squared is 400. 9.8 squared is roughly 100. The square root of 500 should be someplace 25, probably in the 23 range. 22.27. What do we call 22.2? We call the 20 meters per second our x velocity. The 9.8 meters per second is the y velocity. Ooh, nice, Emma. This 22.27 meters per second is our resultant velocity. Emma, what's 806 meters over here? That's the resultant displacement. The resultant part of those two terms tells us that we've put two vectors together to produce one vector. If those vectors are represent displacements, then this is a resultant displacement. If those vectors are representing velocities, then this is a resultant velocity. So this object right here is actually traveling. I don't know if there's two L's in traveling. 22.27 meters per second. How fast is the object actually traveling right there? Cannonball gets shot like that. How fast is it actually traveling right there? 20, right? It's actually traveling 20 meters per second. Take your calculators. Tell me how fast this thing is actually traveling right here. There's only 1 L. 1 L or 2 L's of travel? Brian, what'd you get? How fast is this thing actually traveling right here?
Going didn't get it yet. Sorry.
Oh, what'd you get?
28 meters per second.
Yeah, how'd you do it, Alan?
20 squared plus 19.6 squared times the square root of that.
Yeah, that's our Pythagorean theorem. If this is the initial velocity right here, then we're going to classify this as time equals 0. And then this is at time equals 1 second, and then this is at time equals 2 seconds. This ball is traveling through the air. Analyze these three numbers for me. And there's a problem that we have to address. It's not really a problem, right? But there's a concept that we have to address. Can anybody envision, like, this is an object going through the air, and after 1 second it's traveling 20 meters per second. After 2 seconds, I'm sorry, initially it's traveling 20. After 1 second it's traveling 22.27, and after 2 seconds it's traveling 28 meters per second. Yet for a week or so now, I've said to you that as objects are traveling through the air, gravity changes their speed by how much? 9.8 meters per second every single second. Is that actually true based on these numbers? What does gravity change by 9.8 meters per second every second, Jack? It changes the vertical velocity. If there is no horizontal velocity, like when I just simply drop this thing down, then it's changing the actual velocity by 9.8 meters per second every second. But as soon as there is horizontal and vertical motion, gravity is only affecting the vertical part. If you want to find out the resultant velocity, or how fast this thing is actually going, then we've got to use our Pythagorean theorem, and we find out that it's actually not changing the overall speed by 9.8 meters per second every single second. This is vector math. When we do projectiles, we need our vector math. The worksheet that you have in front of you is just simple practice for you in terms of our projectiles, taking our x velocity and our y velocity, putting them together, and getting the resultant velocity. Okay. Anybody got any questions with that? Okay, so here's what I'm going to do. I'm going to explain a lab that we're going to do starting on Monday. On Monday, I'm going to put you into groups. Today, I'm going to explain this to everybody. And I'm explaining it to you because it's a process-based lab. So sometimes I tell you exactly what to do, and you don't have to figure out a process. Right, so the last lab, like your procedure was like 3 lines long, because I said, hey, roll this thing, take the video analysis, give me these graphs, and interpret the graphs. Like, what you actually had to do wasn't that big of a deal. Today, this lab, one of my favorites, right? We've done it a few different ways throughout the course of the years. We're going to try a different way this time, right? So, here's a ramp. Your group's going to be given this ramp. And then you're going to be given, I don't know, maybe let's say 4 books. Maybe Jolie's group's going to be given 4 books. Maybe Cheryl's group is going to be given 3 books. Maybe Richard's group is going to be given 2 books. Not exactly sure what we're going to do and how we're going to do that. But let's say we're given 3 books. So we make ourselves a ramp with those 3 books. We're going to take this ramp, and you are going to roll some type of ball down the ramp. And when it comes down the ramp, and it rolls on this horizontal table, it becomes a horizontal projectile. Everybody following me there? Okay? Now, I'm going to give you a little target. Your job is to hit the target with the ball. So you're going to put the target down here on the ground. And you're going to hit the target with the ball. The catch is this. I am not going to tell you how far up the ramp you're going to let the ball roll from, or how high the ramp will be until 5 minutes before you have to drop. So Maggie's group might come in and I might say, okay, start the ball 15 centimeters up the ramp and put 2 desks on top of this table to create your horizontal surface. So now her ramp's going to be up here. She's going to put the ball 15 centimeters from the end. She's got to know exactly where to put that thing within 5 minutes. So what's your group going to have to do? Your group's going to have to put together a process to account for all possibilities. Now, the lab that you're going to be passed out on Monday, or really, I probably posted right when you're working on your homework, says you got to have a graph to help you with part of this, and you have to have algebraic expressions already laid out before I ever even give you that information. The lab and the way that it's written up is deliberately vague, because I don't want to tell you exactly what to do, because quite frankly, you might come up with different ways to do it, right? But I might tell you, elevate this with 6 books, drop this thing down here from the top, and we're dropping it from the ceiling. And you got to come up with where you're going to put that target. Right, so your job over the weekend is to have some thoughts when your group gets together on Monday, not starting from scratch on Monday. Huh? So you got those 4 things on Monday. You got 4 questions in the book, and you got this little mental thing for you to do. I'm going to back out of your way here for the last 15 minutes so that you can start working on stuff.